All right, here we go. This is physics reaction video number 43. This is a picture of my old lab assistant. Do a search for Rundquist, Bill Nye, Mall of America, and you'll find lots and lots of stuff. When I did a show with him, I joked that he's my assistant, but I don't think that's who actually did this video. This is I did a search for literally the phrase honors physics and filtered it in the last week. So let's get started.
Hello, ladies and gentlemen. Welcome to our third lesson of this unit, covering the work and kinetic energy theorem. So, in this video, we will be identifying different types of energy, talking about the conservation of energy and looking at different examples of it, and defining kinetic energy and its relation of work. Then we're going to do some examples involving the math. So, what we've learned so far is that work is equal to force times distance. We've also learned that power is the rate that work is done. We just take work divided by time.
So just going to pause here and talk about the presentation. I like the bouncing things that are coming in one at a time. I've talked a lot about teachers sort of covering their page and slowly uncovering it. And this effectively does that. And it never hurts to add a little bit of transitions in there. I know some people roll their eyes at transitions, like the bouncing words or whatever, but I think that it catches the eye, which is kind of the whole point. I also, of course, love this particular slide where he's talking about what they've done in the past, just to say, okay, we have these definitions of work and energy and power, and now we're going to look at different types of it.
By time. Now, our next big concept is energy. Now, energy is the ability for something to do work. Power can be thought of as how quickly that work is done or how quickly energy is used. So an object that has 100 joules of energy has the ability to do 100 joules of work. Now, the law of conservation of energy is that energy can neither be created nor destroyed. It can only be transformed from one form to another.
So I just want to pause on that phrase and thinking about the phrase from the previous slide when he was talking about, can I go back? No, I won't bother. Energy is the ability to do work. And it always gives me pause because I was constantly thinking about energy in quantum mechanics, energy in nuclear energy, certainly in thermodynamics and in mechanics, it's no problem. But as we start to extend to different realms, if you were to say to somebody, oh, that energy term in the Schrodinger equation is that system's ability to do work, it's not as clear. That's what we mean when we talk about energy in those cases. So I guess once more, I'm looking to you guys to help me with that. Is there any problem with, I think I can do it actually, this definition down here in the middle, actually, energy, the ability to do work. And then because for me, it's connected to this statement here, this last one, it can only be transformed from one form to another. Well, if it's the ability to do work, why does it have different forms? Right? You've got kinetic energy. That's your ability to do work, like your ability to smash into something. If you've got potential energy, it's the ability to pull it back down to Earth. And there was an interesting conversation on Twitter a couple of days ago about potential energy belonging to the particle or belonging to the system. And so I just want to keep my eye out for these kinds of things because I think we all know it's way more subtle than all of this because it's made up, right? Energy is not a thing. Energy is just an accounting trick, a really, really useful accounting trick because all that really happens is momentum swaps, right? That's all that our universe is doing. It's all of these, think about like Feynman interactions. It's just things interacting and then going their separate ways, right? And energy is just this phenomenally powerful tool that helps us keep track of stuff. So anyways, keep my eye out for that.
I'll go ahead and pause now if you need to complete this definition. Conservation of
Ooh, that was super cool. Okay, so the idea here is that his students are listening to this, I guess, or watching this live. And I've said this many, many times as my students have said to me, or my colleagues, frankly, oh, students don't learn from video. Video is a waste of time. They're just going to have it on while they, are doing other things. And so I take that criticism to heart. And I spend a lot of time with my students talking about, well, how should you use these videos? And the number one thing I say is you should have a piece of paper and a pencil out, right? If you don't have a piece of paper and a pencil out when you're watching these videos, then you're not right. You're not taking notes. You're not really sort of engaging. Now, some people might say to me right now that I don't have a pencil and paper, but what do I have? I've got my voice, and so I'm actually leaving notes. I'm pausing the video and leaving notes as I do this. And believe it or not, I actually go back to watch these things to remember what was I thinking. And of course, sometimes I find I had missed a point or something, but I really, really loved what he said. Let me pause while you finish that definition. Now, I'd love to hear your thoughts about comparing and contrasting what he did versus let's just hand everything out. Let's give them access to the slides. Let's give them slides with some blanks in it so that they have to fill it out. I think there's lots and lots of different variants of those types of ideas. So I'd love to hear your thoughts about that.
Generation of energy is going to be our biggest concept for this unit. We're definitely going to do some more notes covering just this topic. Now, 6 very common types of energy are nuclear energy, heat energy, mechanical energy, electrical energy, light energy, and chemical energy.
All right, so I'm just going to pause and think about work. Nuclear energy, certainly the way we use it is just to boil water. Right? I mean, I was watching the Chernobyl miniseries again. I've watched it several times because I'm really intrigued by the engineering and human stories there. But there's this really great scene when I can't remember the scientist's name. He just says we use all of that just to boil water. Once we boil water, then we're off and running with just old technology. So I guess from that perspective, we're doing work. Same with heat. Mechanical doing work, I guess, makes sense. Electrical energy is really weird, but ultimately, I guess we only use it to do things like move stuff or light things up. Light rarely is used to do work, but like photosynthesis causes change. And chemical, is it there to do work? Well, I guess rapid exothermic reactions do. But when we think about chemical energy, do we think about that as doing work? So anyways, I'm just challenging people like that. Our initial statement, energy is the ability to do work. Energy seems to be all these really, really interesting, fascinating things going on.
Make sure you write these 6 down. The types of energy that we're going to be talking about in this unit are mechanical energy. So all the types of energy that we're going to be dealing with, specifically kinetic energy today, is a mechanical energy. Let's go over some examples of how energy can be converted into different forms and do work. So the gasoline in your car is chemical potential energy in the molecules. That's converted into kinetic energy and work done by your car. Chemical energy also is stored in dynamite or ANFO and can be used to destroy things like mountains or buildings. Chemical energy is also stored in food. So when you eat it, you convert that into energy that can allow you to do work from your everyday life. Chemical energy is also stored in coal, so when that's burned, then it's converted into work on a steam turbine, which can then be converted into electricity. Sound energy also can do work on your eardrums, which allows you to hear. The gravitational potential energy of water can even be converted to enough electricity to power a city.
So I'm thinking about sound energy. He said sound energy can do work on your eardrum, and that's how you hear. I think other people would say the vibrations in the air, the energy of the vibrations of the air becomes sort of electrical energy in your synapses, auditory nerves. But I guess you do have to do work on the eardrum and on those little tiny 3 bones. I don't know. That's interesting because I think that some people think of it more as a information passing, but I guess it is doing work. And what is he saying here about work done by lights? I'm just going to back it up a little bit.
Energy of water can even be converted to enough electricity to power a city.
Love that. And he didn't talk about lights.
I know we mentioned this a bit yesterday, or not yesterday, but Friday when we were working on our work packet. But when work is done on an object, that object's energy will change. So if positive work is done on an object, that increases that object's energy. But if negative work is done on an object, that decreases the object's energy. So remember, work is not a vector, it is a scalar, but it's that one scalar that can be negative. Negative work just means the energy of the object is decreasing.
I need to think about this for a second. it's that one scalar that can be negative. So a very prevalent scalar in physics is mass, time. I'm going to not use time. Mass and energy, kinetic energy, 1/2 mv squared. Both of those are always positive. So I love that he's pointing out that this is a scalar. It doesn't have any directionality to it, but it can be negative. Man, that's super, super interesting. I never really thought about that. That's really cool.
Now, kinetic energy is the energy of motion. We're going to be talking a lot about kinetic energy this unit. The equation for kinetic energy is 1/2 of the object's mass times the square of its velocity, or Ke equals 1/2 mv squared. The units for kinetic energy have to be based in kilograms, meters, and seconds, but we're just going to end up with joules, just like work.
So kinetic energy is always fascinating to me, right? If you look at the derivation of kinetic energy, it comes from the work energy theorem. And that's why there's this 1/2 in there, because it's an integral. So frankly, this two and this two are totally related to each other based on how the integral works. But if you were to say to students, hey, what's a good way to define the energy of motion? Well, they're gonna talk about mass matters, but especially if you say things like, how would you quantify how dangerous a fast-moving particle is, right? Well, some of them are going to say, oh, momentum. Oh, yeah, but we need another one. This is always a subtle dig that I have about kinetic energy, because it doesn't seem necessary to define or to quantify motion, or the how much motion you have by both momentum and kinetic energy. But it's not going to surprise students to see mass in there and velocity in there. The fact that velocity is in there twice, right? Velocity squared is fascinating, right? And I struggle a lot with that when something's coming to me and going to hit me, right? And I want to know how much. Okay, well, how massive is it? Sorry, I almost said how much does it weigh? How massive is it? And how fast is it going? Those are the two things I want to know to determine how much it's going to hurt me. But it's fascinating to think, well, it's going to either dump a bunch of momentum in me, both the mass and the velocity matter, the mass and the speed, or the mass matters and the speed matters twice as much, right? So that is so weird. But the interesting thing is, even if you could get students to be convinced of that, this 1/2 just seems to come out of nowhere, because we're basically just saying, oh, it's a way to quantify the energy of motion. Let's write it down. But I guess it needs to be connected to all the other ways that you ever achieved that energy in the first place. And that comes from an integral, and that's why there's this 1/2 there. Now, typically, in an introductory class, this is honors physics. I'm not 100% sure what that means. It could mean lots of things, actually. They might not be able to do integrals in this class. And so the 1/2, oh, just take my word for it, the 1/2's in there. Or, it's the usual stuff we wave our hands at, just like the potential energy of a spring has a 1/2 in it because of an integral. So anyways, I'm intrigued by a lot of that.
Meters and seconds, but we're just going to end up with joules, just like work. So the units for kinetic energy are joules. So make sure you get all this written down. Pause if you need to. If we have two pool balls moving towards each other, they're both moving, so they both have kinetic energy. But when they collide, they create sound and a little bit
That's
of
awesome.
So the total amount of kinetic energy after the collision is less than before the collision, because some of that kinetic energy is converted into different forms. So the kinetic energy before is equal to some kinetic energy after, but some of that energy is now heat energy and sound energy.
It's interesting that we say this a lot, and I know I have been guilty of saying this, like, oh, well, if you heard it, a little bit of sound energy there, so it's not totally an elastic interaction. And yet, usually months later, when you finally get to learning about sound and you really start to talk about how to measure the intensity of sound, the sound pressure, the power of sound, you start to realize, if you heard it, if you were pretty close to it, like let's say, arm's length, and it didn't hurt your ears, the amount of sound energy is so small that we basically can ignore it, right? That sound energy is a pretty small piece of the equation that he was talking about right here, right? Heat energy, certainly if you take those steel ball things and you put paper in between, you smash them together, you get a little spark, right? So heat is also true, but I think that's actually also pretty small. So we certainly talk about have students doing, elastic collisions. Let's see, when we say elastic collisions, really all we mean is that the momentum is conserved. No, sorry. No, all momentum is always conserved. So elastic collision energy, we say is conserved. And now we're saying, oh my gosh, geez, I heard it. Oh shoot, I heard it. And so it's not an elastic collision. Man, this stinks, right? So that's my question, I guess, for you guys is there's nothing wrong with this statement. Absolutely a true statement. But if these two terms here are super, super small compared to this one, how useful is it to sort of to warn them about this? I don't know. I'm intrigued by that.
Energy after, but some of that energy is now heat energy and sound energy. Now, unlike momentum, kinetic energy is a scalar. And a scalar, other than work, will never be negative. So it doesn't...
Unless you're particle tunneling, experiencing quantum tunneling. Because when you're inside that barrier, your kinetic energy is negative. I say that because I put a lot of thought into quantum tunneling. You can see my blog post about a new way to calculate quantum tunneling. Maybe I'll try to put a link in. So I love this. I really love what he's doing here. He's like, look, you guys, there's some things we really need to keep our eyes out for. Whereas I told you that work could be negative because sometimes you're adding energy to the system and sometimes you're taking it away. Man, trust me, kinetic energy, come on, 1/2, that's always positive. Mass, that's always positive. Velocity squared, that's always positive because it's squared. So trust me, this is something you can count on. And all I'm saying is that several years later, when they're taking modern physics and they learn about tunneling, they're like, wait, huh? What? What? You're saying that particle can be in the barrier? Well, what does it even mean to be in the barrier? What? And so I'm struck by the students' outrage at tunneling comes from this several years before. And I find that super fascinating. So awesome.
It doesn't matter that these two balls are moving in opposite directions. They both have positive kinetic energy. So kinetic energy is always positive. Now let's relate work to kinetic energy with the work kinetic energy theorem. Make sure you write this all out. The net work on an object causes a change in that object's kinetic energy. The equation is net work equals delta KE, or the final kinetic energy minus the initial kinetic energy. Pause now if you need to finish this slide up. This first example is pretty basic, so I would suggest that you pause now and try it on your own. Otherwise, follow along with me and make sure you write down everything that comes up on this slide. So we have a 25 Newton force that pushes a 3.2 kilogram block 5 meters horizontally across a frictionless table. How much work is done by that force? Well, our equation for work is force times distance, assuming that the force and distance are parallel to each other. In this case, they are, so we don't need to use cosine of an angle. So we just take the 25 newtons of force times the 5 meters of distance, and we get 125 joules of work. Part B.
I'm really intrigued by part B because notice that part A did not need this statement if the block started at rest. Part A did not need it, right? So B's answer is more than just what A has to say, right? And so it's because of the change in kinetic energy. So I love that. But part C does need the started at rest part. So I guess that once the block started at rest, that matters for both B and C.
If the block started at rest, what is the block kinetic energy after 5 meters? So if the block starts at rest, it starts with 0 kinetic energy, no energy of motion. We know that work is equal to a change in kinetic energy, so that positive work from part A is increasing the kinetic energy by 125 joules, so that block now has 125 joules of kinetic energy. And now that we know how much kinetic energy...
So if you're a student and you're like, wait a minute, I never used this 3.2 kilograms. Finally, in part C, you're like, oh, that's when I used 3.2 kilograms. So, right, A and B are independent of how massive the block is. That's fascinating. A and B are independent of how massive the block is. Finally, we get to part C and we need the mass of the block. That's cool.
Energy the block has, we can calculate the speed using our equation for kinetic energy. Remember, kinetic energy is equal to 1/2 mass times velocity squared. So we plug 125 in for the kinetic energy, 3.2 kilograms in for the mass.
I'm going to make my guess here. So 1/2, about 1/2, okay. So 100, about 10 meters per second.
Do a little calculation, and we should get 8.84 meters of speed. Pause here if you need to get the rest of this written down. Now, using the work kinetic energy theorem, we could do some calculations involving the stopping distance of a car. So a car is going to have a certain amount of kinetic energy, but then when it stops, obviously it has 0 kinetic energy. So the kinetic energy that the car had before the brakes were applied is going to be equal to the work done by the brakes. So we can set 1/2 mv squared, the v being the starting speed of the car, equal to force of the brakes times the distance it takes for that car to come to a.
He keeps saying the work done by the brakes. The brakes are part of the car. Yeah, they're going to heat up. I feel like it's the work done by friction, right? Don't you need an external force? Boy, it's so fascinating because if you ask, well, how hot are the brake pads when you're all done? This answer is going to get you there. But if the brakes are part of the car, can you do work on yourself? So how do you, I mean, everyone gets what he's saying here. Everyone understands what he's trying to get at, which is that there has to be an energy transfer somewhere, has to go to somebody. So if the brake pads themselves heat up, will the thermal energy of that equal the initial work of the car? I don't think it would, right? Because if you're in space and you put the brakes on, doesn't do you any good, right? So you need that external actor, the road, to achieve all of this. Yeah, I'd love to hear how you guys think about that because I think it's subtle, but from the perspective of what he's doing with his students here, it's super cool, right? Like, hey, the car had energy. Somebody has to do the work. Who does the work? Well, you stomp on the brakes. So that's the deal. And now let's figure out how much it is. So now let's figure out how much force it takes to bring you to a stop, which is, yeah, basically that's what's going to happen here. Well, I guess if we know the force, we can figure out the distance, whichever you know.
To a stop. So let's say we have a car that's moving at 30 miles per hour. It slams on the brakes, and it takes about 20 feet for that car to come to rest. If that car was going twice the speed, then it's actually going to have quadruple the amount of kinetic energy. Right? If we double the speed, double the velocity, that value is squared, and so the kinetic energy is quadrupled, which means that's going to take quadruple the amount of work or quadruple the amount of distance to bring that car to rest. So,
boy, that's super cool, right? All the objections that I just raised, right, which I'm confused about and wondering the best way to teach it, are independent of this analysis, because this analysis is basically saying, look, you have 4 times the energy, something's got to give. Probably your force is the same because your brakes and the road friction are going to be the same. So all we have is distance to play with. So I love the fact that this particular presentation is almost independent of the confusion that I just raised. So I really, really love that.
So doubling your speed would cause 80 feet before you stop instead of just 40. Now, if we tripled our speed to 90 miles per hour, that's going to multiply our kinetic energy times 9. And so it's going to take 9 times the distance to bring that car to rest.
Okay, I recognize this every time I hear it. I just want to praise it one more time. Doubling things is problematic because multiplying by 2 and squaring the number 2 gives you the same result. Like 2 times 2 is 4 and 2 squared is 4, right? But tripling something is you don't just multiply by 3, you do 3 squared is 9. So I always am happy when you see examples where it says more than just doubling. Tripling is, I think, helps really drive that home because when it was 4, I don't know. Maybe it's just me. 4 obviously comes from the square as well, but 9 really drives it home. I think that we're not just. It's the first time you're like, whoa, it really jumped up. I don't know. I'd love to hear your thoughts about that. I think I'm going to pause here. I think this is great stuff. I really liked this particular representation. I love the animations. I loved the transitions. And I liked how he scaffolded, like, hey, you should pause the video if you need to catch up on this. So lots and lots of really great things. All right. Well, hey, everybody, have a great day. And remember, physics teachers are awesome.